So let's talk through an example where our population data is not normally distributed. So restaurant bills at a given restaurant have an assumed population mean of 32.40. So they're giving us this mean or deviation of 8.16. And this is telling us the data is heavily skewed to the left. So this is telling us that our population data looks something like this, where we have our tail to the left and then most of the data's to the right. The idea being maybe with the restaurant bills, most of the bills are in this range, but maybe some people just come in for one appetizer or one drink, so you have some of these smaller bills coming through as well. So explain why you cannot determine that a given bill will be at least $35. So we have this population mean, we have this population standard deviation. So the idea is, why can't we say we have this distribution here and plug it in to GeoGebra? And the idea is, because our distribution is skewed, we can't use n there. N specifically means that we have a bell-shaped curve. It's nice and symmetric, and we don't have that here. So we can't find probabilities under the curve, we can't go find the probability of at least 35, and it's because our data is skewed. So the population data is not normally distributed. So with that, we can't find probabilities of certain single bills coming through. Like in the previous example where we could find the probability of a single scenario, we can't do that here. Can you estimate the probability that the next 5 bills will average at least $35? So if we work through our conditions, we could talk about independence, could talk about randomization, but let's focus on that sample size condition. So with the sample size condition, it was if our population data was normal, so if we had a nice bell-shaped curve here, sample size wouldn't matter. But what we have here is a sample size of 5, so we have the small sample size coming through, and our population data is skewed. And remember from that simulation, when we had skewed data and a small sample size, we made that distribution of means, it ended up being skewed as well, and we don't want that. We want a nice bell-shaped curve. So for our sample size, remember the rule of thumb is going to be we want a sample size of at least 30, and this is just too small. So, can you estimate this average being at least 35? No, it's because our sample size is just too small. If we take the average of the next 50 bills, would all the conditions be met? So let's talk through each of them this time. Independence. What we're going to say is each restaurant bill is independent, in that the bills aren't going to influence each other. The bill that they receive from one table isn't influenced by the bill from another table, so they're independent of each other. Randomization, again, they don't specifically state that they're taking random 50 bills. In fact, I could even see the argument that because they're taking the next 50 bills, so they're right next to each other, that might not be random. If they're coming from the same time of day, I don't know. So I could start to see the argument here that it's not random, so we shouldn't move forward. But we need to go through this example, so let's just assume it's random. We'll say it's random enough. Let's say it won't change the distribution. And then for our sample size condition, our sample size is now 50, which is more than or equal to 30, so we're good there. So when checking conditions, this is what I'm looking for with the write-up, just kind of state that you have independence. If you're assuming randomization, just state that. And then just be sure to show whatever your sample size is it more than 30 if our population data is skewed. So define the model and draw it. So for here, we're going to have these X values. We're taking the average of 50 bills. So it's going to be the average of 50 restaurant bills. And for our mean, so for the center of our distribution, the mean of the means, again, this is just our population mean. So we just grabbed that $32.40 that was given to us at the beginning. And then for our standard deviation, this is where we calculate, you take the population standard deviation, so that 8.16, and divide by the square root of sample size, which is going to be 50. And this is going to give us a standard deviation of 1.154. So we get this distribution of restaurant bills. When we draw this sampling distribution of means is bell-shaped. And we get that from passing the central limit theorem. So even though our population data look like this, when we take averages of 50 bills from this parent population, it ends up distributing normally, such that it's centered at 32.40, and then if we start moving a certain number of standard deviations away, we end up with our number line. I'm just going to round these a little bit. And we can see where we expect these average bills to land. These between $30 and $35 is where we expect them. So as you can see with these sampling distributions of means, this number line becomes pretty concentrated around the average. So in order to find that are pretty far away from the mean, it's unlikely. As soon as we branch out to like finding the probability of $35 or more, we're getting close to 0% chance. So that happens pretty quickly with these, of getting 0% chance as an answer if we're not close to that mean. So how likely is it that the next 50 bills have an average of at least $35? So using our distribution, so normally distributed, mean of 32.40, standard deviation of 1.154, and we want to find the probability of being at least 35. Meaning if we have our graph here, we're going to wherever 35 is, and we're finding the area above, which should be pretty small. And when we plug this into GeoGebra, we should get out a 0.0121, which means there is a 1.21% chance the next 50 bills have an average of at least $35. So again, in wording, the probability gives us percent chance, and then we have our sample size, so we're taking 50 bills and averaging them. So again, that word mean or average should be coming through, and then of at least $35. For the last one, find the two values for the middle 50% of the average of 50 bills. So if it's the average of 50 bills, we know how those distribute with this normal curve, with this mean and standard deviation. And what we want to do is, with this curve, we're set at that $32.40. We want to find these cutoff points such that we have 50% in the middle. And this is pretty similar to an example in a previous video when we were talking about the normal curve and calculating for cutoff points. If you want this middle 50% and finding it with GeoGebra, what you need to think about are the tails. The fact that if this is our first X value, what happens is this has an area to the left of 0.25. And the second X value has an area to the right of 0.25. So in GeoGebra, what we want to do, if we're trying to find x1, you want to look at the probability of x being less than or equal to something, so we want to create this left tail such that that area is 0.25, and what GeoGebra will give us is 30.62. So that's our x1 value right there. For x2, what we'd want to do is find the probability of x being more than or equal to, so we want to create this right tail over here such that the right tail is equal to 0.25. And what GeoGebra will do is fill in the blank there with a 33.18. So this gives us our lower value of 31.62, upper value 33.18. So this means the middle 50% of the average of 50 bills is between $31.62 and $33.18. So, sampling distribution of means, we figure out how samples from the population behave based on a certain sample size, and once we have that, we can talk about probabilities and cutoff values for averages from a certain sample size.